So now we're going to deal with the strain at a point. So remember that stress is a measure of internal loading at a point. What I mean by internal is we're not measuring the loading that some external body is applying to our chosen body. We're measuring the loads that are applied by the surrounding material to hold it together. Strain is a measure of local deformation at a point. And in this class, but not generally, so this isn't like a material law or anything. This is just with the kind of materials that we deal with, which fortunately are really important kinds of materials. So this is what we can do in this class is an important subset of all the things that can happen in the world. But in, I'm getting ahead of myself. In this class, but not generally, there's a linear relationship between stress and strain. So this is going to be a really important assumption for us that you're dealing with a material and and loading and deformations, like loading and deformation ranges, where these two things are proportional in some way. You know, like there's a linear relationship between these two things. That's called a Hookian relationship. And that comes from the spring relationship that you dealt with in Physics 1. So for a spring, we saw that the force applied to a body by a spring is equal to, I'm going to leave off the negative that you usually use and just write it like this, okay, where F is a load, K is a stiffness for the spring, and X is a deformation. Well, materials in this class will have a relationship that says the stress tensor, and we're going to use the Voigt form for this, is equal to a capital E, that's a matrix, times the Voigt strain. Okay, so what are these things? This is a 6x1, like a 6-element vector-looking thing, representing load. This E is a 6x6 stiffness matrix. And this epsilon is a 6x1 representing deformation. Okay, so it's a matrix form of that Hooke's law. Okay, Hooke's law is not a law. Also, Hooke's law says this: there's a linear relationship between load and deformation for a material that has a linear relationship between force and deformation. That's a pretty crappy law. Okay, and one more thing before I go on to talking about strain. By the way, we'll usually actually use the form that says the Voigt strain is equal to the compliance matrix times the Voigt stress. Where the compliance matrix is the inverse of the stiffness matrix. Your calculator will calculate that inverse for you if you ever need it. Okay, so if you're dealing with steel, would you expect the values in the stiffness matrix to be bigger than 1 or less than 1? Bigger, a lot bigger. It's going to be something times 10 to the 10th or 10 to the 11th. And compliance, would you describe steel as especially compliant? So would you expect compliance values to be less than 1 or bigger than 1? Less than 1, and those are going to be something times 10 to the minus 10. You know. As we go through the definitions of strain, keep this in mind. The methods in this class require really small deformations. For engineering materials, expect strain values, smaller than 10 to the minus 4th. Okay, so there'll be a lot of problems that you'll do, especially in the set of problems on like using the definitions of strain to calculate things, where you're going to get values way bigger than this. You know, you'll get values of a half or something, but that's not realistic at all for like an actual calculation involving any kind of metal or concrete or whatever. Okay. I'll say this again later on, but one of the really important ideas here is that we're dealing with elastic materials, okay? And what an elastic material, so what does it mean when you're, so like you get home, you're all excited, the package is in the mail, you tear it open and there's your new underoos, you know, like your Aquaman underoos, and you put them on and you know, that elastic waistband is making you look so good. So what makes the waistband of your underoos an elastic waistband? The first thought is like, well, it's stretchy, but it's not the stretchiness that makes it elastic, because something made out of Play-Doh can be stretchy. Yeah. Yeah, exactly. The thing that makes it elastic isn't the stretch. It's when you let go, it snaps back. Okay. And so everything that we're doing deals with materials where they deform when you apply forces to them. But when you let go, they turn back, they're back to their original shape. Okay. So yes, you can, metal will stretch, certain metals will stretch 10% before they snap in two. Okay. But this class can't deal with that, because once you get past these strain values of about 10 to the minus 4, you can keep stretching it, but it won't go all the way back anymore. It's a permanent deformation. Okay, so if you see metal bars like at the playground or whatever that have a little bow to them, those are, you know, they're still metal, they're still strong, they haven't broken, but at some point they were deformed past their elastic limit, and now they have a permanent deformation. Okay. Now we're going to get into the strain definitions. Imagine a general deformation of a stress cube. What you have is you start out with a cube, and after the deformation, you end up with a parallelepiped. So each of the sides is a parallelogram. And you can see that the lengths in some dimensions are smaller, and some direct dimensions are bigger. Some angles have gone from 90 degrees to obtuse angles. Some have gone to acute angles. But there are two different kinds of deformations that have happened. So the deformations can be separated into two types. The first one is length changes. There are changes in side length. And these changes are what we're going to call the normal strains. And there are changes in angle between sides. And that's what we're going to call the shear strains. So I'm going to define these two things separately. So first, let's do the normal strains. So let's say that originally, and let's say we're, looking straight on to the XY plane. And let's say that this stress cube has a length capital L0 in each of these two directions. And after the deformation, it's still a rectangle. Because we're not dealing with angle changes yet. But we have a new distance, lowercase l. I'll call this Lx, and I'll call this Ly. Then we'll define the XX normal strain. Notice the notation is like exactly mirrors the notation for stress. That's going to be the quantity, the final length of that side minus the initial, divided by the initial. The YY is lowercase ly minus big L0 divided by L0. And then you can't see it in the picture I've drawn, but you could also look from another side and define the same thing for epsilon ZZ. And that would be lowercase LZ minus L0 divided by L0. Well, based on these calculations, what are the units for strain? Unitless. So you never have to convert strain values, it's just a number. And I said that we're looking for values that are less than about 10 to the minus 4, okay? So 0.0001 or smaller, okay? So this picture I've drawn here, think about this definition. Is that within a reasonable range for an engineering material, or is that too big a deformation? It's way too big. I mean, like, the amount of deformation I have here is about 30% maybe of the original length, right? So you have, so say it goes from 1 to 1.3, 1.3 divided by, no. So it goes from 1 to 1.3. So you got 1.3 minus 1 divided by 1 gives you a strain of like 0.3 instead of 0.0001. So this isn't anywhere near the ballpark. But if I could spend all day trying to draw a deformation that was in that range. If it's visible, it's not in the range that's acceptable, so. Okay, let me do an example. So let's say that we have a piece of material that starts out with a length of 1 centimeter, so 0.01 meters, and a height of 0.008 meters. And I'm using the coordinate system that we're most used to. And then after the deformation, it's gotten longer in the x direction and shorter in the y direction. So let's say in the x direction, this is now 0.011. And in the y direction, this is 0.007 meters. So first we want to calculate epsilon. I'm going to always say EXX and EYY because it's easier to say, but this is an epsilon. So we want to calculate EXX and EYY. And then second, is that an appropriate deformation for this class? Okay, so first, EXX is 0.011 minus 0.01, that's the initial length along that x direction, divided by the initial length along the x direction, and so you get 1 times 10 to the minus third divided by 1 times 10 to the minus second, so 0.10. This is still A. Okay, so EYY is equal to 0.007 minus 0.008 divided by 0.008, and you get negative 1 times 10 to the minus third divided by 0.008. So you get a value of negative 0.125. So B, these strains are way too big. If you're dealing with deformations that big, there's a whole different set of calculations that you have to do. And this class isn't about those. This is just when it's staying inside that elastic range. Okay, well, we've seen one calculation now, and we got positive for one of those calculations and negative for the other one. Can you think of a general rule for the sign of the normal strain? What does it mean if you have a positive normal strain? What does it mean if you have a negative normal strain? That's right. That's right, exactly. So if the thing is stretching, getting longer, you have a positive normal strain. If the thing is being compressed, getting shorter, you have a negative normal strain. So that's an important thing to remember for interpreting this stuff. So notice positive normal strain is stretching. Negative normal strain is, let's call it contracting. Any questions about that? Okay, so now shear strains. So shear strains have to do with the changes in angle between the sides. So these are changes in angle. So if we're using this coordinate system again, and you're starting with a material where all those angles are 90 degrees, then after deformation, remember we said that this thing turns into a parallelepiped, so those always have to be parallelograms. And notice that when we do this, we have two matching angles there that are acute, and two matching angles here that are obtuse. Well, it could be the other, it could be switched the other two, just depending how it's deformed. But there's always two pairs of matching values. Okay, so let's define theta AB as the deformed, so after the deformation, angle between the positive A and positive B face. Okay, so A and B can be X, Y, or Z. Okay, so let's say we want to calculate the deformed angle between the X and Y face. Is that what yeah. Okay, so the X face is this one that's, looks like this. And the positive Y face is this one. Don't use this one and this one because those are the negatives. We want to use the positive X and the positive Y face. Okay, and we're looking for the angle between the positive X and the positive Y face. So after the deformation, this is the positive X face. This is the positive Y face. So this angle here is our theta XY. This is theta XY. Okay. You go to, so let's go around and name all these different faces. This is the positive X. This is the positive Y. This is the negative X. This is the negative Y. Okay. The only two we care about are the positive X and positive Y, and we want to know the angle between those two. You get the wrong answer for theta if you use the positive X face and the negative Y face. Okay. You get the right answer if you use the negatives, but let's not be confusing for no reason. Okay, so then, oh, and I didn't say, we're going to do these in radians. So we're going to give these strains a new name, the Greek letter gamma. Gamma xy is equal to pi over 2 minus theta xy. Gamma xz is pi over 2 minus theta xz. And gamma yz is pi over 2 minus theta yz. And all those angles are in radians, which is not really a unit. It's just really a description of a pure number. So again, these are all unitless. So let's do a quick example. So let's say that, okay, I'm going to use a little bit of a funky coordinate system this time. So let's say that the x-axis is this way and the z-axis is this way. And we go from a rectangular initial shape where all these angles are right angles to a deformed shape where we have something like this, and this angle is 1.43 radians. And all other angles that aren't shown in this picture are unchanged. What are the shear strains? Well, the only plane where there are changes in angle is the xz plane. Okay, so the only non-zero strain is going to be gamma xz. Okay, so gamma xy is equal to gamma yz, and those are 0. Gamma xz is equal to pi over 2 minus the angle between the positive x and positive z face. And what's the angle between the positive x and positive z face? Well, notice that these angles are, what's the word for that, supplementary? Remember that from the SATs or whatever? This and this have to add up to pi. Okay, so the first thing we have to do is identify the positive faces. Okay, this is the positive x face. This is the positive z face. And so the angle we want isn't the one that's given. It's this one. Okay? Everyone with me on that? Well, this angle so theta xz is equal to pi minus 1.43, and you get an angle of about 1.71. And so gamma xz is pi over 2 minus 1.71 which is about negative 0.28. Okay. Again, this is way too big to be realistic for actual strains. And then there's one more question about this, having to do with the signs. So what do you think it means to have a positive shear strain? What do you think it means to have a negative shear strain? We got negative on this one. Yep, that's right. So a positive shear strain means the angle gets more obtuse. Nope. Opposite of that. Means the angle gets more acute. You were thinking about it right, but you had it backwards. For positive. For negative, shear strain, that means that the angle gets more obtuse. Okay, and then how do you put it together into a single description of the state of strain at a point? We don't have a strain tensor. There is such a thing, but not in this class. So the only way we're going to represent it is in the Voigt form. So the Voigt strain, and I'll represent that as epsilon sub v, is EXX, EYY, EZZ, then gamma YZ, gamma XZ, gamma XY. It's the same order as the Voigt stress.